All right, so if you have this continuous polar graph such that, and we're going from alpha to beta, they use that, it's really from A to B, it's the beginning point to the ending point. They just use that because it's in polar, so we use alpha and beta for that. Of, some R equation from alpha to beta is 1/2 integral from alpha to beta, and then it's R of theta squared, d theta. So you take whatever the equation is, that's easy because they're going to give that to you. That's just like the equation, square it, slap a 1/2 out front. The hardest part of these is figuring out what the boundaries are. Okay, if you want to pull out that unit circle, you can do that up until the day of the test, but that's the hard part, because the rest of this, you're just going to memorize the formula. Oh, I square whatever it is they gave me, slap a 1/2 out front. These values are what's hard to find. Okay, so I'm going to talk about finding intersection points real quick. Sketch a graph or look at one. If we're going through the problem together, you can kind of trust me, but you want to look at it and you're like, she always wants us to draw it. A visual helps so much. You can see where they intersect. And then the other thing I want to say about this, an intersection can happen with different coordinates in each graph. And I'm going to show you an example of that. It's strange, but you can have an intersection that's a different amount of rotation for each of the graphs. Do you remember, not last class, but the one before, where I first introduced polar coordinates to you and you guys all had that deer in the headlights look, and I was like, oh, look, this point can be the same as that one, but it's different amounts of rotation. It's like that, okay? And then you also want to check for the pole, which, remember, is our word for the origin whenever you're doing polar equations. Check for the pole because it is 0 theta, where theta is any angle. You can have, 0 comma pi, 0 comma 2 pi over 3, 0 comma pi over 6. It doesn't matter what the amount of rotation is. If your radius is 0, you're at the pole. So that can be any amount of rotation. You just always want to be aware of that as well. And so I'm just going to show you what I mean. We'll just go through one of these. Find the intersection points of r equals 1 minus 2 cosine theta and r equals 1. Well, I mean, think back to like algebra 1, algebra 2. When you wanted to find where two graphs intersected, you set them equal, right? It's the same idea. So we're just going to set this equal to this. I didn't circle that very well. I'm just going to. So we're going to have 1 minus 2 cosine of theta equals 1, and then we'll work that out. So you would subtract over the 1, that's going to give you 0. And so we're just going to set cosine of theta equal to 0. So where on your unit circle, and we're just going to go once around, so there will be 2 answers. Where is cosine going to be 0? Good. Up at the tippy top and down at the bottom. So pi over 2 and 3 pi over 2. So it seems like 2 intersections, right? Let's go ahead and draw it. I like to draw them. I know I'm weird. They turn out pretty. They're like little loop-the-loops. Cool. All right, let's try and plug in 0. If you plug in 0, cosine of 0, that's 1 times 2 is 2. So 1 minus 2, negative 1. So if you're at 0 pi, that's right here, but we went to negative 1, so that's going to be right there. All right, pi over 2, cosine of pi over 2. 0, so 1 minus nothing is 1. So if you go pi over 2, that would be up here, we went 1. So far it looks something like this. All right, now pi, cosine of pi. -1, good. Negatives are going to cancel, so 1 plus 2 would be 3. If you rotate to pi, that's over here. If you go 3 in that direction, that's going to put you right there. So now we're looking something like that. All right, 3 pi over 2. Cosine of 3 pi over 2 would be 0. 1 minus 0 would be 1. So 3 pi over 2 would be down here. If you go 1 in that direction, that's going to put you right here. And then if you plug in 2 pi, that's going to put you back where you start. So it looks kind of like a heart on its side, except like with a like loop the loop inside of it. So that's this graph. R equals 1 is just going to be a circle with a radius of 1. So you would just draw, here, let me make that one a different color. Actually, let me make these 2 different colors. I'm going to make this one green. And I'll make this one pink. So radius of 1, just a circle with a radius of 1. So we only found 2 intersections here, but how many are there? There's 3. This one is the pi over 2. This one is the 3 pi over 2. The reason this one didn't show up is because it's a different amount of rotation for each graph, but we did get a 3rd intersection. Now let's figure out how much rotation it was for each of them. This point right here, for the green graph, that's where we started. So it's at 0 pi for this equation. But it's at a different amount of rotation for the pink graph, the circle that I did. How much did we rotate to get to that intersection for the pink graph? Pi, it's a whole pi, 1 pi for this graph. I don't think this is super likely to happen, but it's just true. And I like to just make sure that I've covered everything. Also, it's kind of cool to me. It's interesting that they can have that extra intersection that doesn't show up because it's at a different amount for each of them. I think that's interesting that happens. I don't know. But anyway, just showing it to you. Also, I don't think it's super likely that you'll have to use one of these formulas, but again, they're just true. And I think it's healthy for you to work out some of these by hand. So we're going to do a couple of them by hand today. I wouldn't spend an overly long time trying to memorize these, but again, they are just true. And so we're going to practice using them and work out a couple of these by hand. On the AP exam, what I think is most likely is that they will give you one of those that says, set up but do not evaluate, you know, those where you just set it up, or they'll have you type it in the calculator and you'll like set it up and then type it in and get the answer. Okay. So find the area of 1 petal of this graph. I'm using example number 7 from the very first polar notes that I showed you. It was that one that had 3 leaves on it. So you know what? Let's type it in the calculator. Let's just practice doing that. Everybody go ahead and grab one. All right, so go to your y equals, but it'll say r equals, and go ahead and type this in. And when you type the X key, it'll put theta there. All right, so go to window. Let's see, I have mine from 0 to pi. I think that should probably be good enough. We'll see if I'm right. This doesn't need to be -10 to 10. Let's maybe make it like -5 to 5. It's a small graph, so you can kind of like bring your dimensions in and then hit graph. I think that was the very first one we graphed, or the second one we graphed on the day where I taught you what polar was, like when we looked at this. So anyway, we're gonna find the area of 1 petal of that. I think it's easiest to just do the first one, but do you see how they all intersect at the pole there? So we need to set this thing equal to 0 to find the amounts of rotation where this will equal 0. Because we want to rotate like from here back around again to get 1 petal. And again, it doesn't matter which petal you choose, but you want to pick like the first one because the numbers are going to be smaller. All 3 are the same. It might not look that way on the calculator because it's like, this is not a very high-tech screen. Like there's not very many pixels and it's not real great. Also, do you notice the screen isn't a perfect square? It's actually sort of a rectangle. So it's like, I promise they're all the same. I know it doesn't really look perfect, but they are, right? So we're gonna need to set this equal to 0. So divide over the 2, that's still just gonna be 0. And so again, we'll need to find places on our unit circle where cosine is 0, except you're not setting theta equal to that, it's 3 theta equals that. And so it'll be pi over 2 and 3 pi over 2. And then to get theta by itself, you would divide over the 3. So what is the first one gonna give us? So pi over 6. And then here the 3's would just cancel and you would have pi over 2. So if we go from pi over 6 to pi over 2, that's going to give us, actually, I think that would give us this leaf, because I believe we started here. Yeah, because I think this is 0 right here. So it would give us actually this leaf right here. You can keep going and you'll get more intersections where this goes to 0, because it's going to keep going around and around like a roundabout forever here, but we only need to find one leaf, okay? So it's going to be 1/2 integral from pi over 6 to pi over 2, and then this thing squared, d theta. Again, oftentimes you would just be asked to set it up, or you would type that in the calculator. I'm going to have us work out a couple by hand today, just to be thorough and because it's healthy for you. And I believe in you, and I think you can find an antiderivative. So let's go, right? First, we have to square this stuff, right? 2 squared. Before, half of that is 2. So we did 2 squared, we got 4, half of that is 2. And then in here we have cosine squared of 3 theta. That's where those little formulas that I gave you come in, because we can't do an antiderivative of cosine squared the way that it is. So do you see this one right here? Cosine squared of theta equals all of this. It's just since ours says 3 theta, you would have, well, no, it'd still be 1 plus, but instead of a 2, there would be a 6. You would have 3 times 2. Okay, thank you for heads nodding. I appreciate that. So it's going to be all of this. And then inside of there, you'll have 1 plus cosine of 6 theta over 2. Which is kind of cool that it's over 2, because now what's going to happen? Yeah, 2's are going to cancel, and now we can do an antiderivative, which this is my whole point, is I just want you to practice doing an antiderivative. So antiderivative of 1. Oh, good. I wanted to see if I knew I get that, because usually people say x. Do you know what I mean? Like it would just be x. But in this case, good. Nice job, guys. Variable is theta. So theta plus, now antiderivative of cosine would be sine. Because there's a 6 there, we would need a 6 out front. So theta plus 1/6 sine of 6 theta. Now we're going to do upper boundary minus lower boundary. We don't really have to simplify it all the way down if it gets super messy, but I want you to do the trig, the unit circle, that's important. If you get a multiple choice question, you're going to have to get through it, all right? So plugging in pi over 2, well, this first part would just be pi over 2. Plus, and then if you plug pi over 2 in here, pi over 2 times 6, that would be 3 pi. So thinking about your unit circle, that would be the same place as pi over on the left side. Sine of that would be 0. So cool, that's just going to be 0. And then let's do the lower boundary. So pi over 6 plus, I think this one's going to be 0 as well. Yeah, if you plug in pi over 6, the 6's cancel, you get pi. Sine of pi is 0. And then that is your final answer. It's always nice when they give you a picture. I always love that, because then you don't have to worry about having a calculator or not. All right, let R be the region in the first quadrant bounded by this polar curve. It's also really awesome that that has a square root over it, because we're about to do what to it? Okay, so that's fantastic. They handed you this one, you know? All right, first thing we have to find are the boundaries though. And same as the one we just did, we're going to set it equal to 0 because we want to go from where it's 0 to where it's 0 again. So let's take this thing and set it equal to 0. So to get rid of the square root, you would square. 0 squared is 0. Then you would divide by 6, but 0 divided by 6 is 0. So you just get sine of 3 theta equals 0. So we are looking for places where sine is 0. Where is that going to happen? Sine's our y value. Good, 0. And I always put 0 pi just to remind myself it's a rotation. And then 1 pi. And then 2 pi and 3 pi and 4 pi. So. And then you would divide by 3. So if 0 divided by anything, just still 0. And then this would be pi over 3. Again, getting the boundaries, in my opinion, getting the boundaries is the hardest part because the rest of it's just 1/2 whatever squared. All right, so setting this up, you'll have 1/2 0 pi to pi over 3, and then square root of all of that squared. Let's make it look a little prettier before we do the antiderivative. First of all, the squared and the square root cancel, like we said, that's really good. 1/2 of 6 will give us 3. So this is 3 sine of 3 theta, d theta. So antiderivative of sine, careful. Negative cosine, good. And you would need a 1/3, but the 1/3 and the 3 cancel. So it'll just be negative cosine of 3 theta such that 0 pi to pi. And so we're going to do upper boundary minus lower boundary. So when, oh, go ahead. Were you going to say something? Oh, I'm sorry. So if you plug in pi over 3, the 3's are going to cancel. Cosine of pi, -1, negatives are going to cancel. So that's just 1. If you plug in 0, anything times 0 is 0. Cosine of 0 is 1. Again, make it negative, it'll be -1. So that actually ends up being 1 plus 1. So 2, that's so neat. The area of that is 2. That's cool. You can disagree, but I'm right. That's so cool. Sean thinks it's cool. Do you want to break or do you want me to keep going and we'll just keep going? All right, find the area between the inner and outer loops of r equals 1 minus 2 sine theta. So first, let's draw a picture so that we can see what is going on. Okay, so let's start by plugging in 0. Sine of 0. 0, right? So 1 minus nothing would just be 1. That's going to be right here. Do pi over 2. Sine of pi over 2 is 1 times 2 would be 2. 1 minus 2, -1. So pi over 2 would be up here, but we went in the negative direction 1, so that's going to put us down here. So far we've got this. Now let's do pi. Sine of pi is 0. 1 minus 0 would be 1. So pi is over here. We went 1 in that direction, so that's going to put us there. So now we have this. Well, to get from there to there, like it's a rotation, so it's going to have to be like circular. So I know it's going to have to go through the pole to get there. And then same thing, to get from this point, like I couldn't connect this way, like it's going to have to keep rotating. Like they're just always going to be like loop the loops. Or I guess you can think of it like you know how your unit circle, like you rotate like this? Like it's always just gonna have to go. I don't know, that's how my brain does it. I'm like, just keep on going that way. Where did I leave off? Okay, 3 pi over 2, sine of 3 pi over 2. -1, negatives cancel, so 1 plus 2 would be 3. So 3 pi over 2 would be down here. If you go 3 in that direction, that's going to put you here. And then 2 pi is going to put you back where you started. So this time it's like a right side up, looks sort of like a heart, like loop the loop. So a little tricky for this one. It says find the area between the inner and outer loop. So hey guys, this is so cool. We're going to find this area. That's neat. Don't lie, you know it is. So not this, just everything outside of it. I know you're excited. So you're gonna have to do the area of the outside one minus the area of the inside one. Let's set it up first, because that's gonna be the easy part. Finding the boundaries is the harder part. It's gonna be 1/2 and then this thing squared, d theta minus, and then write the same thing. We're gonna do the outer loop minus the inner loop. So just go ahead and set it up and then we'll figure out the boundaries. Because again, figuring out those boundaries, like the intersections, that's the hardest part. So again, this is the outer loop, this is the inner loop. Now, all we need to do is set it equal to 0. Do you see why? This is why the picture helps so much. Because the inner loop is going to be from here, rotating around to here, and that's at the pole. Does this make sense? Okay, so we're going to take this and set it equal to 0. And so then what would we do to start solving that? Or I guess you could add this over or subtract the one. It's kind of personal preference, whichever way you want to do that. Either way, the negatives are going to cancel. Divide by 2, you're going to get sine of theta is 1/2. So thinking about your unit circle, there's 2 places where your y value is going to be 1/2. I know I always do that too. Pi over 6. Pi over 4 would give you the root 2 over 2. Five pi over 6, good. I get that you guys are totally at a disadvantage on that. Like it was never something that was directly taught to you. You got thrown in the deep end last year with Calc AB and had to just figure it out. But we did go over a unit circle last time, look back at that. And I will make up problems for you. We'll practice it if you have a question, all right? So those are gonna be the boundaries for the inner loop. Just watch me point to it. If we want the area of this inner loop, we would go from pi over 6, and then it would keep rotating around to 5 pi over 6. So this one goes here, this one goes here. Hey, Ms. Cole, what about the boundaries for the outer loop? I'm so glad you asked. The outer loop is going to start at 5 pi over 6. Like if you think we start here, this was 0 pi, here's pi over 6 to 5 pi over 6, that's the inner loop. The bigger loop takes over at 5 pi over 6. So that's where that one starts. We have to keep going until it ends. Watch me just point to it. Here's 5 pi over 6. We go to pi, 3 pi over 2. Here's 2 pi, and then we go a 6 further. So it's 2 whole pi plus a 6. So it is 13/6. 12/6 would be 2 whole pi. We went a little bit further. It's 2 and a 6. It was like fun with fractions. It's not even calculus, it's just fractions, but I realize that's the hard part, okay? Now, because these are the exact same, I'm only gonna have us do one of them. And I'm going to leave off the boundaries because they're different on each of these. We're just going to do one of them. All right, so if you have 1 minus 2 sine theta squared, that means you have 2 of them. So distributing that all to each other, what's that going to give us? Good, 1 will be the first part, minus. Good, so together that'll be minus 4 sine theta, good. Plus, because negatives are going to cancel, Good, 4 sine squared. I'm only making you write it once because they're identical. Like these are both the same. The only difference is the boundaries, all right? Now we're gonna need to replace this sine squared of theta. You're like, why is she making us do this? She must hate us. No, I just think it's good for you, all right? Sine squared equals this. 1 minus cosine 2 theta over 2. So we're gonna replace that with 1 minus cosine 2 theta over 2. Oh, I'm sorry. I'm really zoomed in because I wanted you all to be able to see it. We're going to simplify that down and then do an antiderivative. So right here, this would be 1/2 times 4. So 2, and then plus 1 up here would be 3. I'm just trying to simplify it all together. So again, this is 1/2 times 4 would be 2, and then 2 plus 1 gives us 3. This minus 4 sine theta is kind of just there. And then for the second part of this, you would have minus 1/2 cosine 2 theta, but again, 1/2 times 4 would be 2. So it'll be minus 2 cosine 2 theta. And now we're going to do the antiderivative, which is what I was getting at. I want you to practice doing an antiderivative. So antiderivative of just 3. Perfect. And I was really worried about that, but that sounds good, you guys. Right? Minus, or actually this will be plus 4 cosine of theta minus, now this would be sine of 2 theta. You would need a 1/2 as an adjustment there, but the 1/2 and the 2 are going to cancel. So it'll just be minus sine of 2 theta. Now, I'm not going to make you write this. The whole point of me going through that was so that you could practice doing an antiderivative. Okay, really sorry. All right, last one, multiple choice, which can be good and bad. 3 of the choices are wrong, right? For the figure above, it shows the curves r equals 2 sine squared of theta and 4 sine squared of theta. So the bigger one is the one that has the 4, the smaller one is the one that has the 2. Does that make sense? Okay. From 0 to pi, oh my gosh. Whenever they give you the boundaries, that is awesome because that's the hardest part to find, right? So when they put this on the paper for you, 0 to pi, that's like awesome. Yeah, that's like, thank you for helping me so much. Well, and then all the choices say 0 to pi, so you almost can't mess that part up. All right, what gives the area of the region bounded between them? So hey guys, this is the area we're finding. That's so cool. That's the area that we're finding. So it's going to be 1/2 integral. Hey, Miss Cole, none of the choices have a 1/2 out front. Oh, but wait, it's just going to cancel with something, right? 0 to pi, you almost don't need to write that because that's what all the choices say. Now we're going to do the outer one, which is the one with the 4. So 4 sine squared of theta squared minus, and then you have to do the inside one, which was the one that had the 2 with it. Do you remember when we did the washer method, or like everybody calls it the donut method? You had the outer one minus the inside one. It's just like that. But now we're going to simplify this down. So this would give us what? 16 sine to the 4th minus, and then 2 squared is 4. So 4 sine to the 4th. Subtract those. So 16 minus 4 would be 12. And then half of 12 is 6. So 0 to pi, 6 sine to the 4th theta d theta. So even if at first it doesn't look like it follows the pattern, it just means it needs to be simplified down. So which choice is that? I think it's the last one. Right? Yeah, D as in dingo.